In this video, I'm going to give you one last overview of everything you've seen during this week's set of topics because I don't want you to get lost in the details. So I just want to give it one more pass through so that you can focus on what's important. So as we're dealing with vector spaces and subspaces, this is probably a really new way of thinking about a lot of mathematics to you because it's not finding a box and putting a number around it. It's more about categorization. So the first big idea here has been vector spaces, which is a new phrase and a scary sounding phrase, but you got to keep in mind that you have been working with vector spaces all of your mathematical life, whether you knew it or not. Whenever you're dealing with real numbers or polynomials or matrices, you're dealing with different categories of mathematical objects that get collected into vector spaces. So what we're going to do here is not worry so much about, hey, here's a collection, demonstrate whether it is a vector space or not. We're going to be happy with the big vector spaces we already know about, like the real numbers, the space of all polynomial functions, or the space of matrices of certain sizes, perhaps. And as long as we're dealing with the usual operations of addition and scalar multiplication as we've always known them, we're just going to take as given that, yeah, these are perfectly good vector spaces. We're not going to worry so much about categorizing vector spaces themselves. So what we do know about each of these groupings and others like them is that they're collections of like things, like matrices collect together, polynomials collect together, and the rules of interaction of them are codified in 10 properties that have to be obeyed. And that makes this collection of things cohesive so that we don't like take two polynomials and add them together and suddenly come back with a matrix, right? That wouldn't make sense. There's rules of engagement with these things. So vector spaces have 10 properties they have to satisfy. We already know what they are based on day-to-day life, particularly with real numbers and with polynomials and things like that. If you want to go explore the weird land of math where you can go back and redefine some of the operations that you're used to using and seeing what happens and what the impact is, then you can go take Math 264, which is the 3-credit version of this class. So rather than worrying about dealing with big vector spaces, we'll just take those as given and then focus on what happens when we go into a particular vector space and select a subset from that space of things that are even more special than just whatever the overall broad category is. So maybe we go into the universe of all polynomials and say, well, you know what, we're just going to collect together all the polynomials of order 5. Or maybe we're going to go into the space of all 4x4 matrices and collect a more special set, which is just the collection of all diagonal 4x4 matrices. Or maybe we go into the real numbers and say, okay, fine, your real numbers, but what I really want to do is gather together all the real numbers that are rational, which means you can write them in fractional form, and that have a 7 in the denominator when you simplify them. When we've formed these more special collections within the bigger vector space, we need to know how to find out if these collections are special enough that they can form their own little mini vector space or subspace. Because they're already part of a big vector space, there's a whole bunch of properties they already inherit. So the only thing we need to do is 2 checks. The 2 things we have to check to demonstrate that some special collection is a formal subspace as opposed to just some collection of stuff is to show that the collection is closed under addition and scalar multiplication. And closure under these operations just mean that when you do the operation with members of this set, you produce another member of the set. Again, we don't want to take a polynomial and add another polynomial and produce, a frog, right? That would not be closed under addition or scalar multiplication. So if we can generate any 2 of the things in the set and add them together, if we get another one back, or if we take a member of this special set and we multiply it by a scalar, and remember a scalar is any real number, like the square root of 5 or 1 over pi or 6 or negative 12, whatever it is. If we take a member of this set and multiply it by a scalar, are we guaranteed to generate another member of this very same set or not? The word any is capitalized here because what we can't do is just take two random individual samples and see what happens to them. We have to formalize the argument to make it clear that we're representing any arbitrary elements from the set under consideration. Now, if we're trying to show that something isn't working, it's okay to just produce one specific concrete counterexample. So here's how not to follow one of these arguments. So let's say we've gone into the vector space of all 3x3 matrices, and we've now collected together, well, we don't just want any 3x3 matrices. We're just going to take in a pile the set of diagonal 3x3 matrices, and we want to show that it's closed under addition. What we can't do is just write down, say, what I've put here on the screen and say, look, there's two diagonal 3x3 matrices, and I added them together, and we produced another diagonal 3x3 matrix, and so ta-da, this set is closed under addition, right? This isn't good enough because maybe we've just accidentally stumbled on a random case where it does work, but there are other cases where it wouldn't. Now, this particular example might make you lean towards believing that it's closed under addition. It may give you a hint as to how you might more generally construct the argument, and here's how it would go. So in this case, I've created two diagonal 3x3 entries, but I've left the entries open as just undefined variables or parameters. So what I'm doing here is I'm representing any two diagonal 3x3 matrices, right? It doesn't matter what A, B, C, D, E, and F are. We see that any two arbitrary 3x3 diagonal matrices will add together and produce yet another diagonal 3x3 matrix. And again, it doesn't matter what specific numbers are in place because we did not put in any specific numbers. And so this is a demonstration that that subset is closed under addition. Or let's say we went into the space of all polynomials, or maybe all second-order polynomials. And then we said, in this big collection, let's make a more special collection. We only want to look at polynomials of degree 2 that don't have the linear term of x to the first. Is this closed under addition? Well, here's an example that indicates it might be closed under addition because I'm showing two of these polynomials with no middle term being added together to produce another similarly structured polynomial. But I can't say, ta-da, the whole space is closed under addition because this is just one example. There might be others where it doesn't work. But again, maybe this leads us to the format that would be the general case where I've taken out specific numbers and just put in representative parameters, and now I'm definitively showing that two polynomials of order 2 with no linear term will add together to produce yet another similarly structured polynomial. And it doesn't matter what numbers are there because I have not put in any particular numbers. I'm just leaving the spot for the coefficients as arbitrary variables. So this would be an argument that the space is closed under addition. Now, once you get your mind around always doing things generally, you actually get to not worry about that if you're trying to show that something isn't true. So for example, let's say we went into the universe or the vector space of all polynomials of order 2, and then from within that space we collected the more special set, all polynomials of order 2, but only the ones whose coefficients are even. Okay, that particular collection would be closed under addition, and maybe for practice you could go off to the side and show that. But is it closed under scalar multiplication? Well, it isn't. And in this case, I don't have to make it general. I just have to show one example that breaks. And here is that example. I'm taking 2x squared plus 2x plus 2. That polynomial is from the space of all polynomials of order 2 that only have even coefficients. And I'm multiplying it by a scalar, which is the square root of 2. And I've produced a polynomial that no longer has even coefficients. So I've taken a member of this collection, I've multiplied it by a particular scalar, and I've generated something that's not part of the set. And this one example, and there's tons of others, but just this one is enough to show that the system isn't closed under scalar multiplication, because here is a case where that fails. So keep in mind, vector spaces is a huge topic. We are going to go with the assumption that the vector spaces are the ones that we've always known and loved. Maybe we're using new terminology, but we work with them as we always have. What we're going to do is dive into these spaces and learn how to demonstrate that a specific smaller collection from within the big collection can be officially called a subspace as opposed to a subset if we can demonstrate that it's closed under addition and closed under scalar multiplication. Those demonstrations require the use of generalized examples, not specific examples. The reason that you need to be able to do this is so that later on, when you get into the deep end of differential equations, for example, the discussion of solution spaces makes sense. And I'll just leave it at that.